Hello, welcome back to EEE 41. This is lecture 12 and we'll introduce metal semiconductor or MS contacts. To properly analyze MS contacts, we need to introduce a new material property called the work function. Our first objective is to define the work function and electron affinity in terms of energy levels. We then proceed by identifying the types of MS contacts and identifying important properties and considerations related to the barrier height for Schottky diodes. Lastly, we should be able to demonstrate how to plot the electric field, voltage, and the EBD of MS contacts in thermal equilibrium. Let's start by taking a look back first on what we know about metals and semiconductors. For metals, we know that the Fermi level is approximately overlapping with the EC, while for the semiconductor, the Fermi level is around between EC and EV for the usual cases of doping concentrations that we are considering. The lower the electron in this energy band diagram, the lower its energy level. Now we introduce this E naught here, where at this high energy level, the electron will now be able to escape the material, and we call that E naught as the vacuum energy level. This E naught is related to the other energy levels, specifically the Fermi level, by what we call the work function, and we will use the symbol capital Phi to represent that work function. So we have different work functions for metals depending on the material, and for semiconductors depending on the material. So phi is basically E naught minus EF. However, for semiconductors, the distance between E naught and EF is actually dependent not only on the material but also on the doping, since the Fermi level moves with the doping concentration. What is constant instead for semiconductors is this chi, or electron affinity, which varies per material, for example, silicon, germanium, gallium arsenide, but is independent of doping. So when we change the doping concentration for our semiconductor, the work function changes, but the electron affinity does not change. So we actually have two types of semiconductors. The first one is what we call the rectifying or Schottky diode, which is created with a lightly doped semiconductor. Its IV curve is similar as that for p-n junction diodes. It follows the Shockley equation, and this is the symbol we use specifically to identify or differentiate our normal p-n junction diodes from Schottky diodes. Now, the metal can either act as the anode or the cathode, meaning the N and the P side always retains its role. So if you look here, for p-n junction diodes, the P always acts as the anode, where the N acts as the cathode. Whereas for metal semiconductor contacts, if you have an N side, it automatically acts as the anode, while if you have a p-type semiconductor, it automatically acts like the anode. So the metal can act like an anode or a cathode. Now, relative to our p-n junction diodes, the advantage of using Schottky diodes is that it has a lower on voltage and it can be switched faster. The disadvantage, however, is that it has a larger reverse leakage current. So it has a larger I naught, but a lower turn-on voltage. Now, not all MS contacts are rectifying or Schottky diodes. Some are non-rectifying or ohmic contacts, and this one is created with the use of a heavily doped semiconductor. So Schottky diodes are created with lightly doped semiconductors, while ohmic contacts are made with heavily doped semiconductors, and its IV curve looks like this one, like a resistor. That's why it's called an ohmic contact. Now, normally we want this MS contact to simply provide a contact for which we can connect wires to our semiconductor devices. So we normally want this one to have very low resistances. And if its resistance is very low, it basically acts like a short. So we use a heavy doping to produce an MS contact that has a low resistance. So this allows us to connect semiconductor devices to metal wires. So for example, we have a P plus N diode and we want to connect it to the, say, the outside world using metal wires, then we'll have to use ohmic contacts on either ends on the device. So if we add a metal here, since this one is already heavily doped, then we expect that this one will produce an ohmic contact and acts like an electrical short ideally. However, for the other end, if we add a metal here, then since this one is a lightly doped semiconductor, then what we'll have here is actually not an ohmic contact, but a rectifying or Schottky diode. And if we want this to be basically our P plus N diode, we don't want another diode here. So what we can do is to actually make this side an N plus region or heavily doped N-type material to make sure that this one acts like a short. Now, the interface between the N and N plus simply acts like two resistances in series, whereas this one is a very small resistance as compared to this one. So ideally, this region here now becomes a short, and as a whole, this would ideally act like our PN junction without any other resistance or diode outside. Now let's consider drawing the energy band diagram for ideal MS contacts, considering that we have an N-type semiconductor. So here the Fermi level is within EC and EI, and let's say we consider Vm is greater than Vs. So let's start with this N-type semiconductor. Vs is the difference between E naught and EF. Now, if we add a metal and put it in contact instantaneously to this N-type semiconductor, then this metal would have a known work function, and that would help us locate the Fermi level at the metal side. Now, with this energy band diagram, we know that the Fermi level is not flat, and therefore the material is not in thermal equilibrium. And what will happen is that charge transfer will happen, and since this side has a lot of electrons, and this is a lower energy level, then most of the electrons would jump into this metal side until it achieves thermal equilibrium. Now, when we draw the energy band diagram at thermal equilibrium, the first thing that we can draw is a flat Fermi level for both the metal and the semiconductor. Now, for the metal, we know that the work function must be constant. It is an intrinsic property of the material, and therefore we can actually locate E naught at this portion. Now, what happens to the semiconductor side? We note that first, E naught is here from the metal, and chi must be constant for the semiconductor. And chi indicates the distance or the energy difference between E naught and EC. And therefore, if we know that E naught is here, then EC must be here by the same distance chi. So what these dots basically represent, the energy levels from this plot at this interface must be the same as when the material is already in equilibrium, or whether in equilibrium or not, these energy differences must be maintained. Now, the charges will transfer from one side to another, but the charges will eventually stop transferring, and far from the junction, or far from the junction or the contact, the N-type semiconductor will retain its original energy band diagram, energy level differences relative to the Fermi level. So the relative differences here should be the same. Now, since EC is at this energy level, at the flat band region or far from the junction, whereas at the interface EC is here, then the only thing that can happen is that the energy band, sorry, EC is here, so the energy band diagram must be bending in this direction. Okay, it cannot bend to that direction and then go flat, so it must bend in this manner. Now, what happens to E naught? We know that chi must be constant, and it is the difference between E naught and EC. EC is here, so we put a constant difference chi at this point. So we know that this here is what we call phi Bn, or the Schottky barrier phi B, and N is to denote that this one is an N-type, and that is equal to phi M. This is phi M minus chi, and what will be left is this one. Now we will note that this semiconductor is what we call a rectifying MS contact because of the presence of this barrier right here, which is rectified or abrupt from this point going to the semiconductor. Okay, in more detail, the Schottky barrier height is the potential energy barrier needed to be overcome by majority carriers to cross the junction. So if I but first take note that in this definition, we actually stated majority carriers. So for this example, since we are dealing with an N-type semiconductor material for our MS contact, then we'll be talking about in terms of electrons. So if I'm an electron at this portion right here, to go to the other side, I need to overcome this barrier right here. So that's why it's called the Schottky barrier. And this is the Schottky barrier height, the height of this energy difference. Now this one is called a rectifying MS contact, since from either ends the electron can actually seize a rectified barrier. So from this one to this point, it sees an increase in energy, whereas from this point to this point, it also sees some energy barrier. However, we define the Schottky barrier height from the metal to the semiconductor. Since from the metal, this is always present, whereas for the semiconductor, we can actually bend this one, and the barrier it sees actually differ. So now we inspect what happens if the work function of the metal is smaller than the work function of the semiconductor for our N-type semiconductor MS contact. Now, since the other one was rectifying, then this obviously should give us the other one, which is non-rectifying or ohmic. Let's start with the energy band diagram instantly after connection. So we start with this flat E naught first. This is our reference energy level, in this case, instantly after connection. Then we draw phi m, or we draw EFM, phi m below E naught. And then at the semiconductor side, we can draw, we can start with EC. And that is chi energy below E naught. Since this one is the one that is constant for our semiconductor. Then relative to EC, we can then draw EI, EV, and EF given the doping concentration. So again, this is consistent to our, say, the case that we're considering that Vs is greater than Vm. So again, when we draw the equilibrium energy band diagram, we start with the flat Fermi level, and then take note the energy levels at the interface. Except for the Fermi level in the semiconductor, since this one is actually the one that actually moves to flatten the two curves at the interface. Okay, so with this small energy difference, we can draw EC. At a slightly larger energy difference below, we draw EI somewhere here, and then EG over 2 below that, we should be able to identify where EV should be in our plot. Given that we know the doping concentration, we can then identify the energy levels here and then basically connect the two end lines. Now, how do we say get a clue on how the energy band diagram will bend upwards or downwards? So we can actually imagine that the Fermi level at the metal stays the same relative to the other. And since this one has a lower energy level instantly after connection, then to flatten the energy band diagram or the Fermi level, then this EBD right here should be bending upwards. So that's why we get this upward bend right here. Okay, so this is our ohmic or non-rectifying MS contact. Why is it a non-rectifying? Since if I look from this side at thermal equilibrium, there is actually no barrier at all. Okay, so the electron here can easily drift to this side right here. However, from the metal, it still actually sees some Schottky barrier, but this time it is actually much smaller. Okay, since we are considering that this one is an N-type, then the Fermi level can only be in this range, and for Vs to be greater than Vm, then EFM must be in between these two, and the possible values that can actually meet that criteria could only lead to very small barrier heights. So still, the barrier it sees at this point is Vm minus chi under this ideal case. Now let's look at another example, a third one. This time we're considering a p-type semiconductor with Vm less than Vs. So again, Vm is the difference between E0 and EF, and that is still true for the semiconductor. Vs is the difference between E0 and EFS. So note that at this point, Vs is actually greater than Vm, and this one here is chi. So let's say we put these two materials in contact, then instantaneously the energy levels must look like this one. Again, our reference is a flat E0, and we draw EFM, chi, Vm below, and EC, chi below this side, and everything follows from EC. Now note that this time the Fermi level at the P side is lower than the Fermi level at the metal. Then what we expect is that this side here must bend upwards to flatten the Fermi level. So after the bending, again, the p-type semiconductor should be bending upwards under this example. And so what now is the barrier height? Now, again, the barrier height is defined for majority carriers, and this time the majority carriers are holes. So if I have a hole right here, it will see a barrier that is equal to this height. Now from this side, it will still see some increasing barrier right here, and it cannot actually smoothly travel from this point to this point, and therefore we note that this kind of um, barrier or bending for holes is our rectifying energy barrier. Okay, and equation wise, this phi bp, or the barrier for holes from the metal side, is equal to chi plus eg minus pm. Now what are the two components to that? First, we have this chi plus eg. So this one is chi, this one is eg, and we will subtract to that this phi m. So if we subtract this one, then we'll get the barrier height. Okay, for our ideal N-type MS contact, we have defined a while ago that the Schottky barrier height must be equal to phi m minus chi. Now, in this diagram, we see here an N-type material. This is our metal right here, and the barrier it sees is phi m minus chi, which is the difference between E naught and EC. However, that is for ideal MS contacts. And what actually happens when we fabricate a real MS contact is that there will be a high density of energy states at the band gap um, at the interface. So ideally, since that must be the band gap, then there must be no energy states right there that the electrons can occupy. However, when we form this MS contact, there actually exists um, some energy levels at this interface that the electrons suddenly are able to occupy. Now, what causes this one? One of them is that, for example, we have a crystalline silicon of some lattice constant, and the lattice constant at the metal side is not perfectly the same. Then, therefore, they will not form the crystal perfectly. Another consideration is that if this one is a diamond lattice in structure and this one is not diamond lattice, then there will be some awkward positions right here at the interface, which will lead to these trapped energy levels or interface energy levels, and that the presence of the electrons at those energy levels actually disturbs the material, the properties of the material at this interface. And what actually happens is that instead of following this equation, the interface works such that the Fermi level is actually pinned at around 0.4 to 0.9 electron volts below EC. So somewhere right here, the Fermi level is pinned, and what actually happens is that the Schottky barrier height does not anymore follow the ideal expectation. So for our ideal MS contact, given that we know phi Bn, given that we know the work function of the metal and the affinity of the semiconductor, we can predict the barrier height, but actually that is not strictly followed when we create actual Schottky diodes. Now let's look at some Schottky barrier heights for some metal on silicon interface or MS contact. Now note that this is the value for electron affinity for silicon, and we have noted a while ago that for N-type materials, phi Bn in the ideal case is phi m minus chi, whereas for the P-type case, phi Bp is chi plus Eg minus phi m. So if we have a metal on its own, we can determine we have these values of the work function of the metal, and therefore if we interface it with our silicon, then we expect that the barrier height for n-type is Vm minus chi. So if we look at this one, 3.12 minus 4.03. So that actually should give us some negative value. But what happens is that phi Bn still is 0.44. So this one is the one that is formed and does not actually follow this one. This one is a bit closer. 4.3 minus 4.03 should give us around 0.27, but what we get is actually 0.5. Okay, so the actual case for the barrier heights actually does not strictly follow these two equations. However, we can still observe some trend right here, since from this equation we see that phi Bn tends to increase with increasing work metal function, since this one is a constant as we are always considering silicon. So higher phi m should lead to higher phi Bn. So higher phi m still gives some higher phi Bn, although not exactly as expected here. Now, for the case of phi Bp, phi Bp tends to decrease this time with increasing work metal function. So as we increase the work metal function, the barrier height that is produced for p-type Schottky or MS contacts actually decrease. So we still get these two trends, although not exactly defined by these two equations. Here we consider Schottky barrier heights for silicide on silicon or silicide-silicon interfaces. Silicides are compounds with silicon, just like oxides are compounds with oxygen. So here we list some common silicides where you can see that the material is composed of silicon with a metallic element. The silicide provides a transition between the metal and the semiconductor and reduces the amount of trapped charges at the interface. With this, the silicon-silicide interface is more stable or easier to control than metal semiconductor interfaces. To create a silicide-silicon contact, first metal is deposited into the silicon. A thermal annealing step is applied where the temperature is increased at a controlled level to allow the reaction between the metal and the silicon to form a silicide layer. In between. Now, the silicon-silicide contact act like metal semiconductor contacts or MS contact, whereas the metal-silicide contact or interface simply act like two conductors in series or in contact. So as a whole, this one is simply one whole MS contact. Now, given that we know the barrier height for our MS contact device, we can then use the depletion approximation where we assume or approximate that the semiconductor is completely depleted within what we call the depletion region up to a depth W. Now, just like what we did in our PN junction diodes, we use this equation. Rho is equal to Q times Nd minus Na. Since at the depletion region there is no more, or there are no more free electrons or holes, so we simply remove plus P minus N here. And therefore, since we have an N-type material right here, then Na is simply 0. So we end up with rho is equal to QND. from 0 to W or at this portion. Now, beyond the depletion region or at the flat band region, we assume that the charge density goes back to 0. And so we end up with a step function in between the two. Now, inside the metal, we know from electromagnetics that there must be no charge inside the metal. So the charge density at this portion must be exactly 0, although there can be a charge at its surface. So we get this plot right here. So from 0 to W, the charge density is QND, and that is constant using the depletion approximation up to a depth W, and suddenly goes back to 0 beyond W. Now we know that this area right here corresponds to the amount of electrons that transferred from this side to the metal. However, for the metal, they cannot be distributed, and therefore they only tend to accumulate at the surface. And so the area of this one must be equal to the area of this one. And this one is an impulse where the delta function represents an area of 1. And we write that with a height equal to this value right here, Q and dW. So the area of this impulse right here is actually Q and dW. And that is also the same as the area here, which is Q and d times W. Using the same approach and starting with the Poisson equation, we can integrate the charge density ρ to get a function that describes the electric field. So we'll also use our expected energy band diagram as a guide. So this one is the Poisson's equation. And so if we want to get the electric field, we can move this delta x right here and integrate both sides to get a function of the electric field. So we are defining this integral right here from 0 to W. And so the ρ at that portion is Q and d, but we have to divide by epsilon s. And we're integrating along x, although we use x prime as a change in variable. Now, one thing we note is that we know that at W, the electric field must already be 0. So here we use that as a reference point. At x prime is or at x is equal to W, the electric field must be 0. And we don't know yet the electric field at this portion, so we just denote that as some electric field as a function of x, and here we use a variable x. Now proceeding with the integral of this one is simply e prime evaluated from 0 to e of x. That gives us 0 minus e of x. The integral of this one is simply q and d over epsilon s times x prime, where x prime is evaluated from W to x. And manipulating that, so the negative sign goes here instead of W minus, and we get W minus x. And therefore, we get this linear equation as a function of x with a positive slope. So we get this one right here. And this one is valid for x is equal to 0 to W. Now what happens to the electric field at this portion? So this one, since this is a metal, we know from electromagnetics that the electric field within the metal must be 0. So we'll have this here and then suddenly get some electric field because of this charge build up right here. Now we proceed and try to get an expression for the depletion layer with. We'll use the voltage function for that. And from the electric field, we can get the voltage using this equation. So we already know the function of the electric field, then we just need to integrate it to get the voltage. So integrating this side with the minus sign, move to the other side, we get dV prime across along some limit equal to negative of the electric field, which is this function here, with some change of variable. Now we go from left to right, and what we know at W is that, let's say we define that the voltage at this point here is 0. So this one is actually different from the one we defined for p-n junctions, where we defined that the voltage is 0 at the left side. However, we will just follow this notation to be consistent with the book. Although this bit of information right here does not actually affect the overall result, since what matters is the voltage difference and not the actual voltage level. Okay, so let's define that the voltage at x is equal to W is equal to 0, and let's get the voltage function with that assumption. So performing the integral, so at this point we can actually have 0 minus Vx is equal to some positive integral, although this one is actually manipulated already to isolate only v of x. Okay, and we get this expression right here where we expect that the result must be quadratic since the electric field is linear. Now, another limit that we can apply to this one is that at x is equal to 0, the voltage must be equal to VBI, since the bending right here must be equal to VBI. Again, VBI is defined when the material is in thermal equilibrium. So if we flip this plot here, we should be able to get this one, and the difference must be VBI. So if this one is 0, this must be minus VBI. So if we use that information, we can substitute this one to be minus VBI, substitute x is equal to 0, and we can actually solve for W, which gives us this expression right here, that W is equal to square root of 2 epsilon over 2 epsilon VBI over QND, whereas the negative actually cancels right here. And from this equation, this one is actually of the same form as what we have with our p-n junction. It is specifically equal to the case where we have a p plus n junction. So this time we can make an analogy that the metal acts like the p plus and the n side acts as the n side. So if we have an ms contact that where the other one is a p-type, so if we have mp, so most of the equations can be made in parallel or compared to that of an n plus p junction. Okay, so these two must be similar in format, and mn must be similar in format with this p plus n. Now let's have some simple practice of how we were able to derive that v of x. Let's show the step-by-step process. Okay, so we copy here the same equation we started. So this is the integral of the voltage is equal to the negative of the integral of the electric field with respect to x. So this one is the function for the electric field. Proceeding with the integral, we'll get here v prime, evaluated from 0 to v of x. We cancel the negative sign, and we end up using this constant right here, q n d over epsilon s. Integral of w is wx prime. The integral of x prime is x prime squared over 2, and we evaluate this from w to x. So here we end up with 0 minus v of x. We copy the constant w times w squared, minus w times x, minus this quantity here evaluated at the two ends, w squared minus x squared over 2. So we get this expression here. So we move the negative sign here, copy the constant, we get a w squared here. Sorry, we actually added a factor 2 over 2 here to be able to factor out this 2 outside. So we get this 2 here, end up with 2w squared minus 2wx minus w squared plus x squared. So here we have 2w squared minus w squared. We end with w squared minus 2wx plus x squared, and factoring out, we copy this constant minus qnd is equal to w minus x squared. And this is the equation presented in the previous slide. So in summary, for our ideal Schottky diode electrostatics with an n-type semiconductor, so here we have an n-type semiconductor. We have defined for the metal its work function, the difference between E naught and EF. For the semiconductor, the constant thing is chi, the distance between E naught and EC, and Vs at the flat band is as originally expected, because if you observe, Vs actually changes along the material, but what we can actually predict easier is this Vs at the flat band. Now the bending or at this interface, assuming that we have an ideal Schottky diode, the barrier height is simply dictated by this one. Vm minus chi would give us the barrier height. Now the next thing we can note is QVBI. QVBI is this height right here, Vbn, minus this height or energy difference right here, which is EC minus EFB at the flat band. Now note that this equation right here can actually be used even if the MS contact is not ideal, meaning even if the material does not follow this one. Okay? So if we know the actual barrier height, we can just proceed with using this equation, since after you've drawn this one, even if this one is not ideal, the built-in voltage will still follow this form. Okay. Now we were able to get the expressions for the electric field and the voltage, but note that with those plots, we actually can get the same equation without using the ideal assumption. So the expressions previously, both for electric field, for voltage, for charge density, all of which can be used even if the diode is does not follow this ideal equation. And so we can, in general, say that the depletion width can be expressed with this formula, square root of 2 epsilon s VBI over QND, where VBI can follow the equation that works even if the diode is non-ideal. We just have to adjust this VBN factor right here. Now for p-type Schottky diodes, so we have here again an ideal Schottky diode. So we have rectifying barrier for both sides of the junction for the majority carriers, which are holes. So for this ideal case, the barrier height is simply chi plus Eg, since in the ideal case this is still chi, so chi plus Eg minus the height here, which is Vm. Now the built-in voltage, again this one can be used even if it is not ideal. Once you already know the barrier height, here we can still follow that the QVBI is equal to VBP minus this energy difference here to get QVBI. And this here is EF minus EV at the flat band region, which can be solved based on the doping concentration. So now VBI is based not only on the doping concentration but also on the barrier height. So the depletion width from the analysis we've done can be shown to be equal to this one. We've just replaced ND with NA. And again, as a last note, the energy band diagram for an ohmic MS contact that is p-type should look like this one. Okay, so we have a p-type semiconductor, but the barrier is non-rectifying. And okay, so that's it for this lecture. Thank you very much.